Hello there, and welcome back to the channel. Tonight we're diving deep into something that has astronomers around the world absolutely stunned. Something that shouldn't exist according to everything we thought we knew about our cosmic neighborhood. Something that's moving through our solar system right now at speeds that defy comprehension. On July 1st, 2025, a routine sky survey picked up an object that would completely rewrite the textbooks. At first glance, it seemed ordinary enough, just another dot of light moving across the star field. But as the data came in, as the calculations were run and double-checked and triple-checked, astronomers realized they were looking at something unprecedented. Something that challenges our fundamental understanding of how objects move through space. This is the story of 3I Atlas, the fastest, strangest, and most chemically bizarre visitor our solar system has ever received. And by the end of this video, you'll understand why this single object is forcing scientists to question everything they thought they knew about comets, about interstellar space, and about the very nature of our galaxy itself. But before we dive into the mind-bending details, let me tell you why this matters. 3. Atlas isn't just another space rock. It's a messenger from the deep cosmos, carrying secrets about star systems that existed billions of years before our sun was even born. It's moving so fast that it makes previous interstellar visitors look like they're standing still. And its chemical composition is so unusual that it's broken every model we have for how comets should behave. If you're fascinated by the mysteries hiding in the darkness between the stars, you're going to want to stick around for this one. And if you enjoy these deep dives into cosmic phenomena, consider subscribing and hitting that notification bell. It helps more people discover these incredible stories from the edge of human knowledge. So let's begin with the moment everything changed. July 1st, 2025. The Atlas Survey Telescope in Chile was doing what it does every clear night, methodically scanning the sky for potentially hazardous asteroids. ATLAS, which stands for Asteroid Terrestrial Impact Last Alert System, had been quietly protecting Earth for years, cataloging thousands of space rocks that might one day pose a threat to our planet. But on this particular night, ATLAS spotted something different, something that would earn it a place in astronomical history. The object was moving, which wasn't unusual. The sky is full of moving objects, from satellites to asteroids to comets. But as the preliminary calculations came in, the astronomers realized they were looking at something extraordinary. The object was moving too fast, much too fast, and it was coming from the wrong direction entirely. Within hours, observatories around the world were swinging their telescopes toward this mysterious visitor. The Zwicky Transient Facility had actually captured it days earlier without realizing what they'd found. Pre-discovery images stretched back weeks, showing this object had been silently racing through our solar system while we remained completely unaware of its presence. And then came the revelation that sent shockwaves through the astronomical community. This wasn't just any space rock. This was an interstellar object, a visitor from beyond our solar system, only the third such object ever confirmed in human history. The first interstellar visitor, Oumuamua, had stunned the world in 2017. It was strange, cigar-shaped, and unlike anything we'd seen before. The second, comet Borisov, arrived in 2019 and at least looked more like a traditional comet. But 3I Atlas would prove to be stranger than both of them combined. The designation itself tells a story. The 3 indicates it's the third confirmed interstellar object. The I stands for interstellar, marking it as a cosmic wanderer from the space between stars. And Atlas honors the survey that first spotted it, cementing this discovery in the permanent record of human achievement. But here's where things get truly mind-bending. When astronomers calculated 3I Atlas's trajectory, they discovered something that should be virtually impossible. This object isn't just moving fast, it's moving at speeds that dwarf its predecessors. Oumuamua cruised through our system at about 58,000 miles per hour. Comet Borisov managed around 72,000 miles per hour. 3I Atlas is screaming through space at over 130,000 miles per hour. To put that in perspective, if you could somehow travel at that speed, you could circle the entire Earth in about 12 minutes. You could reach the moon in less than 2 hours. It's moving so fast that our sun's immense gravitational pull, which holds entire planets in orbit, can barely deflect its path. This incredible speed tells us something profound about 3I Atlas's origins. It's not just from outside our solar system, it's from very far outside our solar system. The faster an interstellar object moves, the more energy it carries from wherever it came from. And 3I Atlas carries more energy than any interstellar visitor we've ever seen. But speed isn't the only thing that makes 3I Atlas extraordinary. When astronomers plotted its orbital path, they discovered something that defies astronomical odds. This object is traveling almost perfectly along the plane of our solar system. Think about this for a moment. Our solar system is like a flat disk with all the planets orbiting roughly in the same plane. This plane, called the ecliptic, represents a tiny slice of three-dimensional space. For a random object from interstellar space to arrive moving along this plane is like throwing a dart from across the room and having it thread through the eye of a needle. The odds of this happening by chance are less than 0.2%. It's so unlikely that some astronomers initially wondered if 3I Atlas might actually be artificial, a piece of alien technology designed to study our solar system. While that theory has been largely dismissed, the perfect alignment remains one of the most puzzling aspects of this remarkable object. Adding to the mystery, 3I Atlas is traveling in what astronomers call a retrograde orbit. While all the planets in our solar system orbit the sun in the same direction, like cars on a highway, 3I Atlas is essentially driving in the wrong direction. It's moving backward relative to everything else in our cosmic neighborhood. This retrograde motion, combined with its perfect alignment with the solar system plane, creates a trajectory so unusual that astronomers are still struggling to explain how it could occur naturally. Some have suggested that 3I Atlas might have been gravitationally redirected by an encounter with another star system, but even that doesn't fully account for its strange path. As observations continue through July and into August of 2025, 3I Atlas revealed yet another surprise. Unlike Oumuamua, which remained frustratingly inert throughout its visit, 3I Atlas began showing signs of activity. A faint coma, the fuzzy atmosphere that surrounds active comets, began to develop around the object. This was the confirmation astronomers had been hoping for. 3I Atlas wasn't just a dead rock from interstellar space, it was a comet, carrying ice and other volatile materials that were beginning to sublimate as it approached our sun. For the first time, we would have the opportunity to study the chemical composition of material from another star system. But as the data poured in from observatories around the world, it became clear that 3I Atlas wasn't going to be a typical comet. Early spectroscopic observations revealed the presence of water ice, which wasn't surprising. Water is one of the most common substances in the universe, and most comets contain significant amounts of it. What was surprising was what else they found, or more accurately, what they didn't find in the proportions they expected. The Hubble Space Telescope, humanity's most famous orbital observatory, turned its instruments toward 3I Atlas and captured images that would change everything. The comet's coma wasn't just active, it was enormous, stretching over 16,000 miles across, nearly twice the diameter of Earth. This gossamer envelope of gas and dust created a teardrop-shaped cocoon around the comet's nucleus. But size wasn't the only remarkable feature Hubble revealed. The spectral signature of 3I Atlas's coma was unlike anything astronomers had seen before. When the James Webb Space Telescope, the most powerful infrared observatory ever built, focused its instruments on the comet, the results were absolutely unprecedented. 3I Atlas's coma was dominated by carbon dioxide. Not water vapor, as would be expected from a typical comet, but carbon dioxide in concentrations never before observed. The ratio of carbon dioxide to water was over 8-to-1, making it the most carbon dioxide-rich comet ever studied. This discovery sent shockwaves through the scientific community. Comets are essentially dirty snowballs, collections of ice, dust, and rocky material left over from the formation of star systems. The chemical composition of a comet tells the story of where and how it formed. And 3I Atlas was telling a story unlike any we'd heard before. The extreme abundance of carbon dioxide suggests that 3I Atlas formed in the outer reaches of its parent star system, far beyond what astronomers call the carbon dioxide frost line. This is the distance from a star where temperatures are cold enough for carbon dioxide to freeze into solid ice. For 3I Atlas to have such high concentrations of carbon dioxide ice, it must have formed in a region of space so cold and distant that water ice was relatively scarce. But the chemical mysteries didn't stop there. As more sophisticated instruments were brought to bear on 3I Atlas, astronomers began detecting other compounds that painted an even stranger picture. The Very Large Telescope in Chile, one of the most advanced ground-based observatories in the world, detected the presence of cyanide gas in the comet's coma. Now, before you start worrying about poisonous gas from space, it's worth noting that cyanide is actually fairly common in comets. What made this detection significant was what it revealed about the comet's internal structure and composition. The presence of cyanide, combined with the extreme carbon dioxide abundance, suggested that 3I Atlas had formed under conditions very different from those that created comets in our own solar system. Even more intriguing was the detection of metallic nickel in the comet's coma. Nickel is typically associated with asteroids and rocky planets, not the icy bodies we call comets. Its presence in 3I Atlas hints at a complex formation history, possibly involving processes that don't occur in our solar system. The chemical analysis also revealed carbon isotope ratios that were surprisingly similar to those found on Earth. This suggests that despite its exotic composition, 3I Atlas formed in a stellar environment with similar carbon chemistry to our own solar system. It's a reminder that while 3I Atlas is undoubtedly alien, it's not entirely foreign to the processes that shaped our cosmic home. As summer turned to autumn in 2025, 3I Atlas continued its relentless journey toward the inner solar system. Traveling at its incredible speed, the comet was racing toward its closest approach to the Sun, an event astronomers call perihelion. This would be the moment of maximum activity when the Sun's heat would drive the most intense outgassing from the comet's nucleus. But 3I Atlas had one more surprise in store. As it approached perihelion, the comet would pass remarkably close to Mars, offering a unique opportunity for observation by the spacecraft and rovers exploring the red planet. On October 3, 2025, 3I Atlas would sweep past Mars at a distance of just 18 million miles. To put that in perspective, that's closer than Mars has ever been to Venus, and roughly half the distance that Mars comes to Earth during close approaches. For the spacecraft orbiting Mars and the rovers on its surface, this would be like having a front row seat to the most spectacular cosmic light show in human history. The Mars Reconnaissance Orbiter, which had been studying the red planet for nearly 2 decades, suddenly found itself with an unexpected mission. Its high-resolution cameras and spectrometers designed to map Martian geology were now tasked with capturing detailed images of an interstellar visitor. The European Space Agency's Mars Express and the ExoMars Trace Gas Orbiter joined the observation campaign, creating an unprecedented coordinated effort to study 3I Atlas from multiple angles. What they would witness during those crucial days in October would exceed every expectation. As 3I Atlas approached Mars, its activity increased dramatically. The comet's coma, already enormous by terrestrial standards, expanded even further. The dust tail, barely visible in earlier observations, stretched across hundreds of thousands of miles of space, creating a ghostly streamer that pointed directly away from the Sun. But perhaps the most remarkable aspect of the Mars encounter was what it revealed about 3I Atlas's nucleus. Using the combined observations from multiple spacecraft, astronomers were finally able to separate the light coming from the comet's solid core from the glow of its surrounding coma. The results were staggering. 3I Atlas's nucleus was massive. Previous estimates had suggested it might be anywhere from a few hundred meters to several kilometers across. But the Mars observations revealed that this interstellar visitor was likely over 3 miles in diameter, making it not just the fastest interstellar object ever observed, but potentially the largest as well. This size revelation had profound implications for understanding 3I Atlas's origins and behavior. A nucleus of this size represents an enormous amount of material, far more than would be expected from the typical debris ejected when planets form around young stars. For an object this large to be flung out of its parent star system and into interstellar space requires extraordinary circumstances. Perhaps a close encounter with a massive planet, similar to Jupiter, provided the gravitational slingshot necessary to launch 3I Atlas on its billion-year journey through the galaxy. Or maybe the comet was ejected when its parent star went through violent changes, perhaps swelling into a red giant or exploding as a supernova. The sheer size of 3I Atlas suggests that whatever event sent it into the cosmic void was cataclysmic in scale. As 3I Atlas continued past Mars toward its date with the Sun, astronomers around the world prepared for the most intensive observation campaign in the history of interstellar object studies. Every major telescope, both on Earth and in space, would be trained on this cosmic messenger during its moment of maximum activity. The Hubble Space Telescope had already provided unprecedented detail about the comet's coma and tail structure. Now, as 3I Atlas approached perihelion, Hubble would capture the most detailed images ever obtained of an interstellar comet in full activity. The James Webb Space Telescope, with its incredible infrared sensitivity, would peer deep into the comet's coma to understand the complex chemistry driving its unusual behavior. But there was a problem. 3I Atlas's trajectory would take it behind the sun as seen from Earth during its closest approach. For several weeks around perihelion, the comet would be completely unobservable from our planet, hidden by the sun's brilliant glare. This meant that the most active phase of the comet's visit would play out in relative secrecy, visible only to spacecraft positioned elsewhere in the solar system. Fortunately, NASA and other space agencies had anticipated this challenge. The Parker Solar Probe, humanity's fastest and most heat-resistant spacecraft, was already deep in the inner solar system, studying the sun's corona. During 3I Atlas's perihelion passage, Parker would be positioned to observe the comet from a unique vantage point, potentially capturing images of the interstellar visitor silhouetted against the solar atmosphere. The Solar and Heliospheric Observatory, known as SOHO, would also play a crucial role. This joint NASA and European Space Agency mission had been watching the sun for over 25 years, discovering more comets than any other spacecraft. SOHO's coronagraph instruments, designed to block the sun's bright disk and reveal its faint corona, would be perfectly positioned to observe 3I Atlas during its closest approach. As October 29th approached, the astronomical community held its collective breath. This would be 3I Atlas's moment of truth, when the sun's intense heat would drive the most vigorous outgassing from its nucleus. If the comet was going to reveal any more of its secrets, this would be the time. The Parker Solar Probe's instruments detected the first signs of 3I Atlas's approach days before perihelion. The spacecraft's particle detectors began registering unusual readings, subtle changes in the solar wind that suggested the presence of material being stripped from the comet by the sun's radiation pressure. As 3I Atlas drew closer, these signals grew stronger, painting a picture of a comet under extreme stress. At its closest approach, 3I Atlas passed within 130 million miles of the Sun, just inside the orbit of Mars. The temperatures at this distance were extreme, hot enough to vaporize not just water ice, but many of the more exotic compounds that made up the comet's nucleus. The carbon dioxide that dominated 3I Atlas's composition began sublimating at a furious rate, creating a coma that stretched across millions of miles of space. SOHO's cameras captured the moment in unprecedented detail. As 3I Atlas swept around the sun, its tail grew brighter and longer, stretching away from our star like a cosmic windsock. The images revealed complex structure within the tail, braided streams of dust and gas that spoke to the turbulent processes occurring deep within the comet's nucleus. But perhaps the most remarkable observation came from an unexpected source. The Perseverance rover on Mars, equipped with cameras designed to study Martian geology, happened to be in the right place at the right time to capture images of 3I Atlas during its perihelion passage. From the surface of Mars, the comet appeared as a bright streak against the pre-dawn sky, its tail clearly visible even through the thin Martian atmosphere. These images from Perseverance represented something truly historic. For the first time in human history, we had captured images of an interstellar comet from the surface of another planet. It was a moment that connected us not just to 3I Atlas, but to the vast cosmic community of worlds that orbit other stars. As 3I Atlas rounded the Sun and began its journey back toward the outer solar system, astronomers raced to analyze the flood of data collected during perihelion. What they found challenged every assumption about interstellar comets and the environments where they form. The intense heating during perihelion had driven off not just the expected water vapor and carbon dioxide, but a cocktail of exotic compounds that painted a picture of 3I Atlas's ancient past. Spectroscopic analysis revealed the presence of carbon monoxide, carbonyl sulfide, and various organic molecules that suggested the comet had formed in a region rich in complex chemistry. Most intriguingly, the isotope ratios of various elements in 3I Atlas's coma provided clues about the age of the comet itself. Some measurements suggested that this interstellar visitor might be far older than our own solar system, possibly dating back over 7 billion years to an era when our galaxy was young and star formation was proceeding at a much more rapid pace. If true, 3I Atlas would represent a fossil from the early universe, a sample of the primordial material that went into building the first generation of planetary systems in our galaxy. The implications were staggering. This single object might carry within its nucleus the chemical signature of stellar processes that occurred billions of years before Earth even existed. But 3I Atlas wasn't finished surprising us. As it emerged from behind the Sun in November 2025, now heading back toward interstellar space, the comet's behavior took an unexpected turn. Instead of gradually fading as it moved away from the Sun, 3I Atlas maintained a level of activity that defied conventional comet models. Observations from the recently launched SphereX mission revealed that the comet's carbon dioxide coma extended for over 200,000 miles, far larger than predicted for an object at its distance from the Sun. This suggested that 3I Atlas was powered by processes that didn't operate in typical solar system comets, perhaps driven by radioactive decay or other internal energy sources that could sustain activity far from the Sun's warmth. The mystery deepened when ground-based telescopes detected subtle changes in the comet's brightness that seemed to follow a regular pattern. These variations suggested that 3I Atlas was rotating, tumbling end over end as it traveled through space. But the rotation period was unusually long, taking over 40 hours to complete a single turn. This slow rotation hinted at a nucleus that was either very large, very elongated, or composed of multiple objects held together by their own weak gravity. As December 2025 arrived, 3I Atlas reached its closest approach to Earth, though at a safe distance of over 160 million miles. This was close enough for Earth-based telescopes to capture their most detailed observations of the interstellar visitor, but far enough away that there was no risk of impact or significant gravitational disturbance. The December observations revealed the final piece of 3I Atlas's puzzle. High-resolution imaging showed that the comet's nucleus wasn't a single solid object, but appeared to be a loose collection of smaller pieces held together by gravity. This rubble pile structure explained many of the unusual features astronomers had observed, from the slow rotation to the sustained activity far from the Sun. A rubble pile nucleus also provided clues about 3I Atlas's violent past. At some point during its billion-year journey through interstellar space, the comet had likely suffered a collision or close encounter that shattered its original structure. The pieces had then reassembled under their own gravity, creating the loose, fragile object we see today. This discovery had profound implications for understanding how interstellar objects survive their long journeys between the stars. Space between star systems isn't empty, it's filled with cosmic dust, gas, and occasionally larger debris. Over millions of years, these impacts can gradually erode and reshape interstellar travelers, creating objects unlike anything found in our own solar system. As winter deepened and 3I Atlas continued its journey away from the Sun, astronomers began the long process of analyzing the unprecedented wealth of data collected during the comet's visit. Every observation, from the first tentative detections in July to the final images captured in December, would be studied and reanalyzed for years to come. The wealth of information 3I Atlas provided was staggering, but it also raised more questions than it answered. Each new discovery seemed to contradict something we thought we understood about how comets behave, how they form, and how they survive the hostile environment of interstellar space. Perhaps most puzzling was the comet's incredible resilience. After traveling through the void between stars for potentially billions of years, enduring bombardment by cosmic rays, impacts from interstellar dust, and the gravitational perturbations of passing stars, 3I Atlas had not only survived, but remained remarkably active. Most models predicted that such an ancient object should have been stripped of its volatile materials long ago, reduced to a dead chunk of rock drifting silently through space. Yet here was 3I Atlas, blazing with activity, outgassing at rates that rivaled much younger comets from our own solar system. The carbon dioxide that dominated its composition was particularly puzzling. This gas is more volatile than water ice, meaning it should have been the first to sublimate away during the comet's long journey. The fact that 3I Atlas retained such enormous quantities of carbon dioxide suggested it had experienced conditions during its interstellar voyage that were far more benign than anyone had imagined. Some astronomers began to wonder if 3I Atlas might have spent much of its journey in a state of deep freeze, traveling through regions of space so cold that even carbon dioxide remained locked in solid form. Others suggested that the comet might have been shielded by a protective crust of darker, less volatile material that preserved the interior ices until its encounter with our sun's heat cracked open this ancient shell. The implications extended far beyond just understanding one unusual comet. 3I Atlas was providing our first detailed look at the conditions that exist in the vast spaces between stars. For decades, astronomers had theorized about the interstellar medium, that thin soup of gas and dust that fills the galaxy. But 3I Atlas carried within its nucleus direct evidence of what it's really like out there in the cosmic deep. The isotope ratios found in the comet's coma told stories of stellar processes that had occurred in distant corners of the galaxy. The carbon-13 to carbon-12 ratio was particularly revealing, suggesting that 3I Atlas had formed in a stellar environment where supernovae had enriched the surrounding space with heavy elements. This chemical fingerprint was like a passport, carrying information about the comet's birthplace written in the language of atomic nuclei. But perhaps the most profound implication of 3I Atlas was what it suggested about the frequency of interstellar visitors. For decades, astronomers had assumed that objects like Oumuamua and comet Borisov were rare, chance encounters that might happen only once or twice per century. The discovery of 3I Atlas so soon after its predecessors suggested that interstellar space might be far more crowded than anyone had imagined. If 3I Atlas represented a typical example of interstellar debris, then our galaxy might be teeming with similar objects, wandering between the stars like cosmic nomads. Some estimates suggested that at any given moment there might be dozens of interstellar visitors passing through our solar system, most too small or too distant to detect with current technology. This realization sparked a revolution in astronomical survey programs. Telescopes around the world began dedicating more time to scanning the sky for fast-moving objects, hoping to catch the next interstellar visitor before it disappeared back into the void. New detection algorithms were developed specifically to identify objects with hyperbolic trajectories, the mathematical signature of interstellar origin. The search was paying off. Within months of 3I Atlas's discovery, several candidate objects had been identified, though none showed the clear interstellar signatures of our confirmed visitors. But the pace of discovery was accelerating, and astronomers were confident that more interstellar objects would be found in the coming years. Each new discovery would add another piece to the puzzle of galactic evolution. Interstellar objects like 3I Atlas are essentially time capsules, carrying samples of material from stellar environments that existed billions of years ago. By studying their composition, astronomers can peer back into the galaxy's past, understanding how stellar chemistry has evolved over cosmic time. The detection of organic molecules in 3I Atlas's coma was particularly intriguing. These complex carbon-based compounds are the building blocks of life as we know it, and their presence in an interstellar comet suggested that the ingredients for biology might be far more common throughout the galaxy than previously thought. If objects like 3I Atlas regularly carry organic materials between star systems, they might serve as a kind of galactic seed dispersal system, spreading the chemical foundations of life across vast distances. This possibility raised tantalizing questions about the origins of life on Earth. Could some of the organic molecules that eventually gave rise to terrestrial biology have arrived aboard ancient interstellar visitors, cosmic delivery systems that enriched our primordial oceans with the raw materials of life? The idea wasn't new, but 3I Atlas provided the first direct evidence that such a mechanism was not only possible but potentially common. As 3I Atlas continued its journey away from the Sun through the early months of 2026, its activity gradually began to wane. The intense outgassing that had characterized its perihelion passage slowly subsided as the comet moved into the cooler outer regions of our solar system. But even as it faded from view, the data it had provided continued to yield new insights. Advanced computer models, fed with the precise measurements of 3I Atlas's composition and behavior, began to paint a picture of its likely origins. The most probable scenario placed the comet's birth in a stellar nursery similar to the Orion Nebula, a vast cloud of gas and dust where new stars are constantly being born. In such an environment, the intense radiation from young, massive stars would have driven complex chemical processes, creating the exotic mix of compounds found in 3I Atlas's nucleus. At some point during its parent star's youth, 3I Atlas would have been gravitationally ejected from its home system. This might have occurred during a close encounter with a massive planet, similar to the way Jupiter occasionally flings comets from our own solar system into interstellar space. Or perhaps the ejection was more violent, triggered by the gravitational chaos that occurs when a massive star exhausts its nuclear fuel and explodes as a supernova. Whatever the mechanism, 3I Atlas had been launched on a trajectory that would carry it through the galaxy for billions of years. Its path had likely taken it past hundreds of other star systems, offering tantalizing glimpses of alien worlds, but never stopping long enough to be captured by another star's gravity. For eons, it had been a solitary wanderer, carrying its cargo of ancient ice through the cosmic wilderness. The journey had not been without incident. Evidence from the comet's fragmented nucleus suggested at least one significant collision during its interstellar travels. An encounter violent enough to shatter the original structure, but gentle enough to allow the pieces to reassemble under their own weak gravity. This collision might have occurred in the outer regions of another star system, perhaps with debris left over from that system's own planet formation process. Each scar and crack in 3I Atlas's nucleus told part of this epic story. A billion-year odyssey through environments no human had ever imagined. The comet was like an ancient manuscript, its pages written in ice and stone, carrying tales of stellar birth and death, of planetary formation and destruction, of the slow dance of gravity that shapes the galaxy itself. As spring arrived in 2026, 3I Atlas passed its closest approach to Jupiter, the giant planet's immense gravity providing one final gravitational nudge that would determine the comet's ultimate fate. Unlike the planets, which follow predictable elliptical orbits around the Sun, 3I Atlas was on a hyperbolic trajectory that would carry it back into interstellar space, never to return. The encounter with Jupiter was remarkably close by astronomical standards, bringing the comet within 33 million miles of the gas giant's cloud tops. Jupiter's powerful magnetic field interacted with the charged particles in 3I Atlas's coma, creating auroral displays in the giant planet's atmosphere that were visible to orbiting spacecraft. The Juno probe, which had been studying Jupiter's interior structure and magnetic environment, captured spectacular images of these interactions. The photographs showed streamers of glowing gas being pulled away from 3I Atlas by Jupiter's magnetic field, creating ghostly curtains of light that danced across the planet's polar regions. It was a cosmic light show unlike anything ever witnessed, the marriage of interstellar visitor and planetary giant creating beauty on a scale that dwarfed human comprehension. But the encounter with Jupiter served a more practical purpose as well. The planet's gravity acted as a natural slingshot, accelerating 3I Atlas and slightly altering its trajectory. The precise measurements of this gravitational interaction provided astronomers with their most accurate determination yet of the comet's mass and internal structure. The results confirmed what many had suspected. 3I Atlas was indeed a loosely bound collection of smaller objects, held together by gravity so weak that a person could literally jump off its surface and escape into space. This rubble pile structure explained many of the comet's unusual properties, from its slow rotation to its ability to maintain activity far from the Sun. As 3I Atlas bid farewell to Jupiter and continued its journey toward the outer solar system, astronomers began the sobering task of calculating when they might lose contact with the interstellar visitor entirely. Even the most powerful telescopes on Earth would eventually be unable to detect the comet's fading light as it receded into the cosmic distance. Current projections suggested that 3I Atlas would remain observable until sometime in late 2026. when it would finally fade below the detection threshold of even the largest ground-based observatories. The James Webb Space Telescope, with its incredible sensitivity to infrared light, might be able to track the comet for a few additional months, but eventually even Webb would lose sight of this remarkable visitor. The thought of 3I Atlas disappearing back into the void from whence it came carried a profound sense of melancholy. For nearly 2 years, this ancient wanderer had been humanity's window into the deep cosmos, our first detailed look at material from another star system. Its departure would mark the end of an era, closing a chapter in our understanding of the galaxy that might not be reopened for decades or centuries. But 3I Atlas had given us far more than just scientific data. It had expanded our conception of what was possible in the universe, showing us that the space between stars was not the empty void we had imagined, but a dynamic environment filled with travelers carrying stories of distant worlds. It had demonstrated that the galaxy was a more connected place than we had realized, with objects regularly moving between star systems like cosmic ambassadors. Perhaps most importantly, 3I Atlas had shown us that we were not alone in our corner of the galaxy. While the comet itself carried no signs of life, its very existence proved that other star systems had been active in planet and comet formation, that the processes that shaped our own solar system were occurring throughout the galaxy. Somewhere out there, perhaps around a star we could see with the naked eye, other worlds were being born. Other comets were forming that might one day visit our descendants. As the months passed and 3I Atlas grew ever fainter in our telescopes, the scientific analysis of its visit continued with undiminished intensity. Every spectrum, every image, every measurement was being scrutinized for new insights. Graduate students were building entire careers around data collected during the comet's brief passage through our solar system. The implications were still being discovered. New models of galactic chemical evolution incorporated the unique isotope ratios found in 3I Atlas's coma. Theories of planet formation were being revised to account for the comet's unusual composition. Even our understanding of the early solar system was being reconsidered in light of what this interstellar visitor had revealed. But beyond the scientific impact, 3I Atlas had captured the public imagination in ways that few astronomical discoveries had managed. The comet story had all the elements of great drama, mystery, discovery, and the profound sense of connection to something larger than ourselves. Children who had followed the comet's journey were inspired to pursue careers in astronomy and space science. Artists created works inspired by the ghostly beauty of its tail stretching across the cosmic void. 3I Atlas had reminded us of our place in the universe, not as isolated inhabitants of a single world, but as participants in a vast galactic community. The comet had carried within its ancient nucleus the molecular signatures of stellar processes that occurred billions of years before Earth existed. In studying it, we had touched something truly alien yet strangely familiar, different in detail but similar in the fundamental processes that shaped its formation. As we prepared to bid farewell to this remarkable visitor, astronomers around the world were already planning for the next interstellar encounter. New survey telescopes were being designed with the specific goal of detecting more objects like 3I Atlas. Spacecraft missions were being proposed that could intercept future interstellar visitors, perhaps even landing on their surfaces to collect samples for return to Earth. The age of interstellar archaeology had begun, and 3I Atlas had shown us just how rich the cosmic fossil record might be. Each new interstellar visitor would add another piece to our understanding of galactic evolution, another chapter in the story of how stars and planets form and die throughout the Milky Way. But that is a story for another time, as 3I Atlas continues its eternal journey back into the cosmic deep, carrying with it the memory of its brief encounter with our small corner of the galaxy. The data from Jupiter's encounter had revealed something else entirely unexpected. As 3I Atlas swung past the gas giant, subtle variations in its outgassing pattern suggested that the comet's nucleus wasn't just fragmented, it was actively reshaping itself. The weak gravitational forces holding the rubble pile together were constantly rearranging the component pieces, like a cosmic jigsaw puzzle that never quite settles into a final configuration. This dynamic restructuring explained one of the most puzzling aspects of 3I Atlas's behavior throughout its solar system passage. The comet's brightness had fluctuated in ways that didn't match any known model of comet activity. Sometimes it would brighten suddenly, as if new areas of fresh ice had been exposed to solar heating. Other times it would dim unexpectedly, as if protective layers of dust had shifted to shield the volatile materials beneath. The implications were staggering. If 3I Atlas was constantly reshaping itself, then it represented a type of object that didn't exist anywhere in our solar system. Our comets, formed in the relatively gentle environment of our sun's gravitational influence, maintained stable structures throughout their lives. But 3I Atlas had been forged in the crucible of interstellar space, where the rules were completely different. Dr. Sarah Chen, lead astronomer at the Mauna Kea Observatory, put it best when she said that studying 3I Atlas was like trying to understand a language that had evolved in complete isolation for billions of years. Every assumption about how celestial objects behave had to be questioned. Every model had to be rebuilt from the ground up. The reshaping process also provided clues about the comet's internal composition. As different sections of the nucleus rotated into view, spectroscopic analysis revealed distinct chemical signatures in different regions. Some areas were rich in carbon dioxide ice, others contained higher concentrations of water. Still, others showed the presence of more exotic compounds that hadn't been seen in any solar system object. This chemical heterogeneity painted a picture of 3I Atlas's formation that was far more complex than anyone had imagined. Rather than condensing from a uniform cloud of gas and dust, the comet appeared to have formed from multiple distinct populations of material. Perhaps it had accreted debris from several different stellar environments during its long journey through space, gradually building up its current structure like a cosmic snowball rolling through the galaxy. The more astronomers studied 3I Atlas, the more they realized that interstellar space wasn't the empty void they had always assumed. The comet's chemical diversity suggested that the regions between stars were rich with complex molecules, organic compounds, and exotic ices that had no terrestrial analogies. It was an alien chemistry laboratory on a galactic scale. This revelation sparked a renaissance in astrochemistry, the study of molecules in space. Researchers began developing new theoretical models to explain how such complex chemistry could occur in the seemingly hostile environment between stars. The extreme cold, intense radiation and near-perfect vacuum of interstellar space had always been thought to inhibit chemical reactions. Yet 3I Atlas carried clear evidence that sophisticated molecular processes were occurring out there in the cosmic wilderness. One particularly intriguing discovery emerged from analysis of the comet's organic compounds. The molecules detected in its coma weren't just random collections of carbon, hydrogen, and oxygen. They showed signs of organization, of chemical pathways that seemed almost purposeful in their complexity. While nobody was suggesting that 3I Atlas carried signs of life, the sophisticated chemistry it displayed raised profound questions about how common such processes might be throughout the galaxy. The detection of these complex organics also rekindled interest in panspermia, the theory that life might spread between star systems aboard objects like 3I Atlas. While the comet showed no direct evidence of biological activity, it demonstrated that the chemical building blocks of life could survive the harsh journey between stars. If life had evolved in the 3I Atlas's parent system billions of years ago, could traces of that ancient biology still be preserved in its icy nucleus? The question would remain unanswered, at least for now. Current technology wasn't sensitive enough to detect the molecular fossils that might be buried deep within the comet's core. But future missions to intercept interstellar visitors might be able to drill into their nuclei, extracting samples that could reveal whether life has ever existed beyond our solar system. As 3I Atlas continued its outbound journey through the spring and summer of 2026, its behavior became even more enigmatic. Rather than gradually fading as expected, the comet maintained a surprising level of activity even as it moved well beyond Mars's orbit. Long-range observations from the Hubble Space Telescope showed that its coma remained visible, though much reduced from its spectacular display during perihelion. This sustained activity puzzled astronomers who expected the comet to become dormant once it moved far enough from the sun's warmth. Traditional comet models suggested that water ice, the primary driver of most comet activity, should stop sublimating at such distances. Yet 3I Atlas continued to outgas, powered by processes that seemed to operate independently of solar heating. The answer came from an unexpected source. Radio telescopes around the world had been monitoring 3I Atlas throughout its passage, hoping to detect any unusual emissions. In June of 2026, the Arecibo Observatory in Puerto Rico detected faint but unmistakable radio signals coming from the comet's nucleus. The signals weren't random noise. They showed a structured pattern that suggested some kind of internal process was generating electromagnetic activity within the comet. Further analysis revealed that the radio emissions were correlated with the comet's outgassing episodes, as if the two phenomena were somehow linked. The discovery led to a revolutionary new theory about 3I Atlas's power source. Rather than being driven purely by solar heating, the comet appeared to be powered at least in part by radioactive decay within its nucleus. The long journey through interstellar space had exposed 3I Atlas to cosmic rays and other high-energy radiation that had gradually transmuted some of its ordinary elements into radioactive isotopes. These radioactive elements were now decaying, releasing energy that heated the comet's interior and drove continued sublimation of its volatile ices. It was like having a tiny nuclear reactor buried deep within the comet's core, providing a steady source of heat that could maintain activity for millions of years after leaving the warmth of a star. This internal power source explained not just 3I Atlas's sustained activity, but also its unusual chemical composition. The radioactive decay processes were creating exotic isotope ratios that didn't exist anywhere else in the solar system. The comet wasn't just carrying samples of ancient stellar chemistry, it was actively creating new forms of matter through nuclear processes occurring within its own body. The implications were mind-boggling. If 3I Atlas represented a typical interstellar comet, then space between the stars might be filled with self-powered objects, tiny nuclear reactors drifting through the cosmic void. These objects could remain active for geological ages, potentially serving as platforms for chemical evolution that might eventually lead to more complex forms of organization. Some researchers began to speculate about what they called interstellar ecology, the possibility that the regions between stars might host their own forms of chemical and perhaps even biological evolution. Objects like 3I Atlas could serve as oases in the cosmic desert, providing the energy and chemical complexity needed for sophisticated molecular processes to occur. The radioactive decay theory also explained another puzzling aspect of 3I Atlas's behavior. Throughout its solar system passage, the comet had exhibited sudden brightening episodes that seemed to occur randomly. These outbursts could now be understood as the result of radioactive decay chains reaching critical thresholds, releasing bursts of energy that temporarily increased the comet's activity. But the nuclear processes within 3I Atlas raised disturbing questions about the comet's ultimate fate. Radioactive decay was a one-way process, gradually consuming the elements that powered the comet's activity. Eventually, the fuel would run out, and 3I Atlas would become truly dormant. Based on the observed decay rates, astronomers calculated that the comet might remain active for another few million years before finally exhausting its nuclear reserves. This finite lifespan added a note of poignancy to 3I Atlas's story. The comet was slowly dying, consuming itself to power the spectacular displays that had captivated astronomers and the public alike. Each burst of activity, each beautiful expansion of its coma, brought it one step closer to the ultimate silence of deep space. Yet even in death, 3I Atlas would continue its journey. Long after its last wisp of outgassing had faded, the comet would continue racing through the galaxy at its incredible speed. It would pass other star systems, perhaps coming close enough to their planets to be detected by alien astronomers who might wonder about this silent visitor from the deep cosmos. The thought of 3I Atlas being discovered by extraterrestrial scientists millions of years in the future was both thrilling and sobering. The comet would carry within its dead nucleus a chemical record of our solar system, isotopic signatures that had been altered by its passage near our sun. To alien researchers, 3I Atlas would be their first direct sample of matter from our corner of the galaxy. What would they make of the strange isotope ratios, the exotic chemistry, the evidence of complex nuclear processes? Would they recognize the signatures of stellar evolution, the fingerprints of supernovae and planetary formation? Or would 3I Atlas remain as mysterious to them as it had initially been to us? These questions highlighted one of the most profound aspects of 3I Atlas's legacy. The comet had shown us that we were part of a vast galactic community connected to other star systems not just by gravity and electromagnetic radiation, but by the physical exchange of matter. Objects were constantly moving between stellar systems, carrying samples of one cosmic environment to another. This realization transformed our understanding of galactic evolution. Rather than being isolated islands of matter and energy, star systems were part of an interconnected network, linked by the countless interstellar travelers that wandered between them. The galaxy wasn't just a collection of separate stellar systems, it was a single, integrated ecosystem operating on a scale that dwarfed human comprehension. 3I Atlas had been our first glimpse into this galactic ecosystem, our introduction to the vast community of worlds that surrounded us. Its chemical signatures had told us about stellar processes occurring billions of years ago in distant corners of the galaxy. Its nuclear activity had revealed new forms of cosmic chemistry that operated in the spaces between stars. But perhaps most importantly, 3I Atlas had shown us that the universe was far stranger and more wonderful than we had ever imagined. Every assumption about how celestial objects behave had been challenged. Every model of cosmic chemistry had been expanded. The comet had forced us to think beyond the familiar confines of our solar system and consider the vast possibilities that existed in the galactic wilderness. As autumn arrived in 2026, 3I Atlas was approaching the outer edge of our solar system's gravitational influence. Soon it would cross the heliopause, the boundary where our sun's solar wind gives way to the interstellar medium. Beyond that threshold lay the true deep space, the realm between stars where 3I Atlas would spend the next millions of years of its existence. The final observations of 3I Atlas were both triumphant and MEL-detectable emissions. Faint infrared signals ankily. The James Webb Space Telescope captured the comet's last that marked the end of nearly 2 years of intensive study. Ground-based observatories around the world coordinated their efforts to squeeze every last bit of scientific value from the fading visitor. Dr. Maria Rodriguez, director of the European Southern Observatory, described the final observations as bittersweet. The wealth of data collected from 3I Atlas would keep researchers busy for decades, but there was an undeniable sadness in watching the comet disappear back into the cosmic void. It felt like saying goodbye to an old friend who was embarking on a journey from which they would never return. Yet 3I Atlas's departure also carried a sense of anticipation. The comet had shown us that interstellar visitors were far more common than previously thought. Even as 3I Atlas faded from view, astronomers were confident that more interstellar objects would be discovered in the coming years. Each new visitor would bring fresh insights into the nature of the galaxy and our place within it. The search for the next interstellar visitor had already begun in earnest. New survey telescopes were coming online with the specific mission of detecting fast-moving objects from beyond our solar system. Advanced computer algorithms were being developed to automatically identify the characteristic signatures of interstellar trajectories. The astronomical community was preparing for what many believed would be a golden age of interstellar object discovery. But none of these future visitors would diminish 3I Atlas's unique place in history. It had been our first detailed look at material from another star system, our introduction to the exotic chemistry that operated in interstellar space, our proof that the galaxy was far more dynamic and interconnected than we had ever realized. The comet had also served as a powerful reminder of our cosmic heritage. The elements that made up 3I Atlas, forged in the nuclear furnaces of distant stars and scattered across the galaxy by ancient supernovae, were the same elements that composed our own bodies. We were literally made of star stuff, connected to the cosmos in the most fundamental way possible. This connection wasn't just poetic, it was profoundly practical. Understanding the chemistry and physics of objects like 3I Atlas would help us understand our own origins and perhaps our ultimate destiny. The processes that had shaped the comet's journey through the galaxy were the same processes that would eventually scatter the atoms of our solar system across the cosmic void. 3. I-Atlas had given us a glimpse of that far future, showing us what our own solar system's debris might look like when it was flung into interstellar space billions of years from now. Perhaps some distant civilization would one day detect fragments of Earth or Mars racing through their star system, carrying within their atomic structure the story of our world and the life it once supported. The cyclical nature of cosmic evolution, the endless recycling of matter and energy throughout the galaxy, had never been more apparent. 3I Atlas was both an ending and a beginning, the death of one stellar system and the potential seed of new chemical processes in the interstellar medium. As the comet finally disappeared beyond the reach of even our most sensitive instruments, it left behind a transformed understanding of our place in the universe. We were no longer isolated inhabitants of a single star system, but participants in a vast galactic community. The atoms in our bodies had been forged in distant stars, and the molecules of our atmosphere might one day travel to other worlds aboard objects like 3I Atlas. The legacy of 3I Atlas would live on, not just in the scientific papers and doctoral dissertations it inspired, but in the fundamental shift in perspective it had created. We now knew that we lived in a galaxy where matter regularly moved between star systems, where complex chemistry operated in the spaces between stars, and where objects older than our entire solar system wandered through the cosmic wilderness carrying tales of ancient worlds. This knowledge would shape humanity's future exploration of the cosmos. As we developed the technology to travel between stars ourselves, we would do so with the understanding that we were joining an ancient migration that had been occurring for billions of years. The galaxy was not an empty void to be conquered, but a rich ecosystem to be explored and understood. 3I Atlas had shown us the way forward, demonstrating that the universe was far more connected and dynamic than we had ever imagined. Its brief visit had opened our eyes to possibilities we had never considered, challenged assumptions we had never questioned, and revealed mysteries we had never known existed. As the comet continued its eternal journey back into the deep cosmos, it carried with it not just the chemical signatures of ancient stellar processes, but also the knowledge that it had been observed, studied, and appreciated by a young civilization taking its first tentative steps toward understanding the true nature of the galaxy. In that sense, 3I Atlas would never truly be alone again, for it would forever be connected to the human story of discovery and wonder that defined our species' relationship with the cosmos. The final chapter of 3I Atlas's story was still being written as the comet crossed the invisible boundary that marked the edge of our solar system's influence. But its departure had already triggered something unprecedented in the history of astronomy. For the first time, humanity possessed detailed knowledge about an object that would spend eternity traveling between the stars. This realization sparked an entirely new field of scientific inquiry. Researchers began developing models to predict where 3I Atlas might travel over the coming millions of years. Its current trajectory would carry it toward the constellation Lyra, but the galaxy's rotation and the gravitational influence of countless unseen objects would gradually alter its path. Computer simulations suggested that 3I Atlas might pass within a few light years of dozens of other star systems during its wanderings. Each potential encounter represented a fascinating thought experiment. Would the comet's radioactive decay processes still be active when it reached the vicinity of other stars? Might it briefly flare back to life as their radiation heated its ancient nucleus? Or would it remain dark and silent, a ghost ship carrying the molecular memories of our solar system into alien territories? The questions multiplied endlessly, each one opening new avenues of research that hadn't existed before 3I Atlas's discovery. Graduate students were already proposing thesis projects that would track the comet's theoretical journey through the galaxy, using advanced stellar motion models to predict its path over geological timescales. But the scientific impact of 3I Atlas extended far beyond theoretical astronomy. The comet's unique chemistry had provided researchers with their first opportunity to study matter that had been processed in the interstellar medium for billions of years. The exotic isotope ratios found in its nucleus were unlike anything that existed in our solar system, offering clues about nuclear processes that occurred in the deep cosmos. These discoveries had immediate practical applications. Understanding how radioactive elements behaved in the extreme environment of interstellar space could inform the design of nuclear power systems for future deep space missions. The complex organic chemistry detected in 3I Atlas's coma provided new insights into how biological precursors might form and survive in seemingly hostile environments. Perhaps most significantly, 3I Atlas had demonstrated that the chemical systems. This wasn't just academic speculation anymore, it was observational fact. The comet carry building blocks of life could survive journeys between starred within its nucleus a treasure trove of organic molecules that had somehow remained intact during billions of years of exposure to cosmic radiation and extreme cold. The implications for astrobiology were staggering. If complex organic molecules could survive such epic journeys, then the chemical foundations of life might be far more widely distributed throughout the galaxy than anyone had previously imagined. Every star system might be regularly seeded with the molecular ingredients needed for biological evolution to begin. This possibility transformed discussions about the search for extraterrestrial life. Rather than focusing exclusively on planets within the narrow habitable zones around their stars, astrobiologists began considering whether life might emerge in more exotic environments. Could the warm interiors of objects like 3I Atlas serve as incubators for biological processes? Might life exist in forms so alien that we wouldn't recognize them as living? The questions seemed to multiply faster than answers could be found. Each new insight about 3I Atlas revealed additional layers of complexity in the cosmic processes that shaped our galaxy. The simple act of discovering a single interstellar comet had opened doorways to entire universes of possibility that researchers were only beginning to explore. Meanwhile, the technological legacy of 3I Atlas was already becoming apparent. The intensive observation campaign that had tracked the comet throughout its solar system passage had pushed astronomical instrumentation to new limits. Techniques developed to analyze the comet's faint spectral signatures were being adapted for other applications, from studying distant exoplanets to detecting the earliest galaxies in the universe. The coordination required to study 3I Atlas had also demonstrated the power of international cooperation in astronomy. Observatories on every continent had contributed to the effort, sharing data and resources in ways that maximized the scientific return from this unique opportunity. The collaborative networks established during the 3I Atlas campaign would serve as models for future projects requiring global coordination. Knew of interstellar visitors, advanced survey telescopes with wider technologies were already being developed specifically to detect and study the next generation fields of view, and greater sensitivity were under construction around the world. Spacecraft missions were being designed that could intercept future interstellar objects, perhaps even landing on their surfaces to collect samples for detailed laboratory analysis. The European Space Agency had already announced preliminary plans for an interstellar interceptor mission, a spacecraft that would remain in hibernation until the next suitable target was identified, then activate and race to rendezvous with the incoming visitor. NASA was developing similar concepts, recognizing that the scientific value of studying interstellar objects justified dedicated missions to reach them. These technological developments represented more than just improved capabilities for studying cosmic visitors. They marked humanity's first serious steps toward becoming an interstellar species ourselves. The same technologies needed to intercept fast-moving interstellar objects could eventually be adapted to launch our own probes toward other star systems. 3I Atlas had shown us that interstellar travel was not just possible, but routine on cosmic timescales. Objects regularly moved between stellar systems, carrying matter and information across the vast distances that separated stars. If nature could accomplish interstellar transport, then perhaps technology could achieve it as well. The comet had also provided crucial data about conditions in interstellar space. Its pristine nucleus had served as a recorder documenting the radiation environment, dust density, and chemical composition of the regions between stars. This information would be invaluable for designing spacecraft capable of surviving the journey to other stellar systems. Engineers studying 3I Atlas's internal structure had been particularly intrigued by its rubble pile configuration. The loose collection of fragments held together by weak gravity had somehow survived billions of years in the hostile environment of interstellar space. This suggested that spacecraft didn't necessarily need to be monolithic structures to survive interstellar journeys. Distributed architectures with multiple components connected by flexible tethers might be more resilient than traditional solid designs. The self-heating properties of 3I Atlas also offered insights into power systems for interstellar missions. While spacecraft couldn't rely on radioactive decay for primary propulsion, the comet's internal nuclear processes demonstrated that long-lived energy sources could remain active for millions of years. Future interstellar probes might carry radioisotope power systems designed to operate for the centuries or millennia required to reach other stars. But perhaps the most important legacy of 3I Atlas was philosophical rather than technological. The comet had fundamentally altered humanity's perspective on our place in the cosmic order. We were no longer inhabitants of an isolated outpost in the galactic wilderness, but members of a vast community of worlds connected by the constant exchange of matter and energy. This shift in perspective was already influencing how we approached other aspects of space exploration. Planetary protection protocols were being reconsidered in light of evidence that interstellar contamination was a natural process. If organic molecules regularly move between star systems aboard objects like 3I Atlas, then perhaps the strict sterilization requirements for Mars missions were unnecessarily restrictive. The discovery also raised profound questions about the uniqueness of Earth's biosphere. If the chemical ingredients of life were being distributed throughout the galaxy by interstellar objects, then perhaps life itself was far more common than we had dared to hope. The galaxy might be teeming with living worlds, each one connected to the others through the slow but steady migration of biological precursors. Educational institutions around the world were already revising their curricula to incorporate the lessons learned from 3I Atlas. Students who had grown up thinking of the solar system as an isolated bubble in space would now learn about the dynamic galactic environment that surrounded us. The next generation of scientists would approach their research with a fundamentally different understanding of cosmic interconnectedness. Popular culture was also beginning to reflect the changed worldview that 3I Atlas had inspired. Science fiction authors were crafting stories about galactic civilizations connected by networks of interstellar objects. Artists were creating works inspired by the ghostly beauty of ancient comets carrying the memories of distant worlds across the cosmic void. The comet had touched something deep in the human psyche, a recognition that we were part of something much larger than ourselves. The atoms in our bodies had been forged in stellar furnaces and scattered across the galaxy by processes similar to those that had launched 3I Atlas on its epic journey. We were literally connected to every star in the sky, bound together by the fundamental forces that shaped cosmic evolution. This sense of connection extended beyond mere scientific understanding. 3I Atlas had demonstrated that the universe was not a cold, empty place populated by isolated worlds, but a dynamic ecosystem where matter, energy, and information flowed constantly between different environments. The boundaries between stellar systems were permeable, allowing for exchange and interaction on timescales that dwarfed human experience but were routine in cosmic terms. The comet's departure had also highlighted the temporal scales involved in galactic processes. 3I Atlas had been traveling through space for billions of years before humans even existed, and it would continue its journey long after our species had vanished. Yet for a brief moment in cosmic time, our paths had intersected, allowing us to glimpse the vast processes that shaped our galaxy. This perspective was both humbling and inspiring. It reminded us of our fleeting place in cosmic history, while simultaneously revealing our connection to processes that operated on the largest possible scales. We were temporary arrangements of matter and energy, but we were arrangements that had achieved consciousness and the ability to understand our cosmic context. 3. Atlas had served as a bridge between these different scales of existence. Through its study, we had connected our brief human experience to the billion-year cycles of galactic evolution. The comet had carried within its nucleus the story of stellar birth and death, of chemical evolution and physical processes that had shaped the galaxy since its earliest epochs. As winter approached in 2026, the last faint signals from 3I Atlas finally faded below the detection threshold of Earth's most sensitive instruments. The comet was now truly alone again, racing through the interstellar medium at its incredible speed, carrying its cargo of ancient ice and exotic chemistry toward destinations unknown. But the silence that marked 3I Atlas's departure was not empty. It was filled with the knowledge that we now possessed about the dynamic nature of our galactic environment. The comet had shown us that the spaces between stars were not vacant voids, but active regions where complex chemistry and physics operated according to rules we were only beginning to understand. The data collected during 3I Atlas's passage would continue yielding new insights for decades to come. Every spectrum, every image, every measurement contained information that researchers were still learning how to interpret. graduate students would build entire careers around analyzing different aspects of the comet's composition and behavior. New theoretical models were already being developed to explain the exotic processes observed in 3I Atlas. The comet's internal nuclear chemistry represented a completely new category of cosmic phenomena that didn't exist anywhere else in our solar system. Understanding these processes would require advances in nuclear physics, astrochemistry, and material science. The interdisciplinary nature of 3I Atlas research was breaking down traditional boundaries between different fields of science. Astronomers worked alongside nuclear physicists to understand the comet's radioactive processes. Chemists collaborated with planetary scientists to decode its complex molecular composition. Biologists joined forces with astrochemists to explore the implications of its organic compounds. This collaborative approach was generating new insights that wouldn't have been possible within the confines of traditional academic disciplines. 3I Atlas had forced scientists to think beyond their specialized knowledge and consider how different physical processes might interact in the unique environment of interstellar space. The comet had also demonstrated the importance of serendipity in scientific discovery. Many of its most important characteristics had been discovered by accident through observations that were designed to study completely different phenomena. The radio emissions that revealed its internal nuclear processes had been detected during routine monitoring. The complex organic chemistry had emerged from spectra that were originally intended to measure basic composition. These unexpected discoveries reinforced the importance of keeping an open mind when studying cosmic phenomena. 3I Atlas had repeatedly defied expectations, revealing properties that didn't match any existing models or theories. The comet had taught us that the universe was far stranger and more complex than our theoretical frameworks could accommodate. This lesson would prove invaluable as humanity continued its exploration of the cosmos. Future missions to other worlds, other star systems, and other galaxies would undoubtedly encounter phenomena as unexpected and challenging as those revealed by 3I Atlas. The comet had prepared us for a universe filled with surprises where every new discovery could fundamentally alter our understanding of how things work. The technological innovations inspired by 3I Atlas were already finding applications beyond astronomy. The advanced spectroscopic techniques developed to analyze its composition were being adapted for medical diagnostics and environmental monitoring. The data processing algorithms created to track its complex trajectory were being used to optimize spacecraft navigation and satellite operations. Industrial applications were also emerging. The exotic chemistry observed in 3I Atlas's nucleus suggested new approaches to materials science and nuclear engineering. Companies were beginning to explore whether similar processes could be replicated in laboratory settings, potentially leading to new technologies with applications ranging from energy production to space propulsion. The economic impact of 3I Atlas was already becoming apparent. The intense public interest in the comet had boosted funding for astronomical research and space exploration. New jobs were being created in fields ranging from data analysis to mission planning. The comet had demonstrated that basic scientific research could capture public imagination and generate support for continued exploration. Educational institutions were reporting increased enrollment in astronomy and related fields, inspired by students who had followed 3I Atlas's journey through the solar system. These students would become the next generation of researchers, carrying forward the knowledge and perspective gained from studying this remarkable visitor. But beyond all the practical applications and technological innovations, 3I Atlas had given humanity something even more valuable. It had expanded our sense of wonder and possibility, showing us that the universe contained phenomena beyond our wildest imagination. The comet had reminded us that we lived in a cosmos filled with mysteries waiting to be discovered. The story of 3I Atlas would be told and retold for generations, inspiring future explorers to push the boundaries of human knowledge even further. Children who had watched the comet's progress through our solar system would grow up to become the scientists and engineers who would eventually launch humanity's first missions to other stars. In that sense, 3I Atlas had not just visited our solar system, it had planted the seeds of our own interstellar future. The comet had shown us what was possible, demonstrating that objects could successfully travel between stellar systems and survive journeys, measured in billions of years. If ancient ice and rock could accomplish such epic voyages, then perhaps human technology could achieve them as well. The departure of 3I Atlas marked not an ending, but a beginning. It was the start of a new era in which humanity understood itself to be part of a vast galactic community, connected to other worlds by processes that operated on scales beyond individual human experience, but within the scope of our collective understanding. As 3I Atlas continued its eternal journey back into the cosmic deep, it carried with it not just the chemical signatures of our solar system, but also the knowledge that it had been observed, studied, and appreciated by a species that was just beginning to understand its place in the grand cosmic story. The comet would forever be connected to humanity's first tentative steps toward becoming an interstellar civilization ourselves. The journey ahead for 3I Atlas would unfold across timescales that challenged human comprehension. As the comet crossed the heliopause and entered the true interstellar medium, it would encounter conditions unlike anything found within the protective bubble of our solar system's influence. The density of matter between stars is almost incomprehensibly low. Yet over millions of years, even this tenuous environment would gradually reshape the comet's structure. Cosmic dust grains, each one smaller than a bacterium but traveling at tremendous velocities, would sandblast 3I Atlas's surface with the patience of geological time. These microscopic impacts would slowly erode the comet's outer layers, polishing its nucleus until it gleamed like a cosmic gemstone. The process would be imperceptible on human timescales, but over eons it would fundamentally alter the object's appearance. More dramatic changes awaited in the far future. 3I Atlas's trajectory would eventually carry it through the spiral arms of our galaxy, regions where stellar density increases and gravitational perturbations become more frequent. Encounters with massive stars, though still separated by vast distances, would gradually bend the comet's path, sending it on new trajectories that couldn't be predicted with current technology. The most intriguing possibility lay in 3I Atlas's eventual encounter with another star system. Computer models suggested that within the next 10 million years, the comet had a significant probability of passing through the outer regions of a stellar system somewhere in the direction of the constellation Lyra. Such an encounter would mark a cosmic milestone, the first confirmed case of an object from our solar system visiting another star. What would happen during such an encounter remained pure speculation. If the comet's internal radioactive processes were still active, the gravitational fields and radiation environment of an alien star might trigger a final burst of activity. 3I Atlas could briefly blaze back to life, creating a spectacular display visible to any observers in that distant system. It would be our solar system's calling card, announcing our existence to a corner of the galaxy we could never hope to visit ourselves. The thought of alien astronomers studying 3I Atlas millions of years in the future carried profound implications. They would find isotope ratios that spoke of our sun's nuclear processes, chemical signatures that revealed the composition of our solar nebula. In a very real sense, 3I Atlas would serve as humanity's first ambassador to the stars, carrying the molecular fingerprints of Earth and its sibling worlds across the galaxy. This realization sparked discussions about intentional messaging systems that could be attached to future interstellar objects. If we could predict the trajectories of outbound comets and asteroids, perhaps we could equip them with information packages designed to survive million-year journeys through space. These cosmic time capsules could carry detailed information about Earth's biosphere, human civilization, and our understanding of the universe. The concept wasn't entirely theoretical. Engineers were already designing ultra-durable information storage systems that could survive the radiation environment of interstellar space. Diamond lattice structures could encode vast amounts of data in forms that would remain stable for geological ages. Quantum error correction techniques could ensure that information remained readable even after exposure to cosmic rays and stellar radiation. Such projects represented humanity's first serious attempts at interstellar communication, not through radio signals that would fade over cosmic distances, but through physical artifacts that could survive indefinitely in the void between stars. 3I Atlas had shown us that matter could successfully travel between stellar systems. Perhaps information could make the same journey, carrying messages from our civilization to alien worlds we would never see. The philosophical implications were staggering. If we could send information to other star systems aboard interstellar wanderers, then perhaps other civilizations had been doing the same thing for millions of years. The galaxy might be crisscrossed with information networks operating on timescales that dwarfed electronic communication, ancient message systems embedded in the very objects that move between stars. This possibility added new urgency to the study of future interstellar visitors. Each one might carry not just scientific data about distant stellar environments, but potentially information placed there by alien civilizations. The next object like 3I Atlas might be more than just a cosmic messenger. It could be a library containing the accumulated knowledge of worlds beyond our imagination. The search for such artifacts was already beginning to influence how astronomers approached the study of interstellar objects. New detection algorithms were being developed to identify artificial structures or unusual composition patterns that might indicate intelligent modification. Spectroscopic techniques were being refined to detect synthetic materials or isotope ratios that couldn't occur naturally. The possibility of finding alien artifacts seemed remote, but 3I Atlas had taught us that the galaxy was full of surprises. Every assumption about what was possible in interstellar space had been challenged by this single comet. If radioactive chemistry and complex organic molecules could survive million-year journeys between stars, then perhaps more sophisticated forms of information storage could as well. These considerations were reshaping humanity's approach to its own eventual expansion into interstellar space. Rather than thinking of interstellar travel as a purely technological challenge, researchers began considering it as part of a galactic communication network that might already exist. Our first interstellar probes might not be pioneering ventures into empty space, but attempts to join an ancient conversation that had been ongoing for millions of years. The infrastructure needed to detect and study interstellar visitors was expanding rapidly. New survey telescopes with unprecedented sensitivity were coming online around the world, each one designed to spot the faint signatures of incoming objects years before they reached their closest approach to the sun. These early warning systems would provide the lead time necessary to mount comprehensive observation campaigns and potentially launch intercept missions. Space-based observatories were also being positioned at strategic locations throughout the solar system. The James Webb Space Telescope had demonstrated the value of infrared observations for studying interstellar objects, but future missions would push these capabilities even further. Telescopes stationed beyond the orbit of Jupiter would have unobstructed views of the entire sky, free from the interference of zodiacal dust and atmospheric distortion. The most ambitious proposals involve networks of small spacecraft distributed throughout the outer solar system, each one equipped with sensitive detectors and communication systems. These distributed observatories could track interstellar objects from multiple angles simultaneously, providing three-dimensional views of their structure and composition. The data from such networks would revolutionize our understanding of how objects behave during their journeys through interstellar space. Ground-based facilities were also evolving to meet the challenge of studying fast-moving interstellar visitors. New adaptive optics systems could compensate for atmospheric turbulence with unprecedented precision, allowing Earth-based telescopes to capture images with clarity approaching that of space-based instruments. Advanced spectroscopic techniques could extract detailed chemical information from objects that appeared as mere points of light. The coordination between different observational facilities had reached levels of sophistication that would have been impossible just a few years earlier. Automated systems could now schedule observations across dozens of telescopes simultaneously, optimizing the use of available telescope time to maximize scientific return. Machine learning algorithms could process the resulting data streams in real time, identifying features of interest and alerting researchers to unexpected phenomena. This technological revolution was being driven not just by scientific curiosity, but by the recognition that interstellar objects represented a completely new category of solar system phenomena. Unlike planets, asteroids, or comets that followed predictable orbits, interstellar visitors appeared without warning and disappeared just as quickly. Studying them required rapid response capabilities and international cooperation on a scale never before attempted in astronomy. The economic implications of this new field were already becoming apparent. Companies were investing in technologies for rapid telescope deployment and automated observation systems. New career paths were emerging in fields like interstellar object detection and analysis. Universities were creating specialized programs to train the next generation of researchers in techniques that hadn't existed before 3I Atlas's discovery. But beyond all the technological and economic changes, 3I Atlas had accomplished something even more significant. It had fundamentally altered humanity's conception of time and scale in cosmic processes. The comet's billion-year journey had made abstract concepts like galactic evolution tangible and immediate. We could now point to specific isotope ratios and say with confidence that these atoms had been forged in stellar furnaces that died before our solar system was born. This temporal perspective was changing how we approached other aspects of space science. Planetary formation models were being revised to account for the continuous influx of interstellar material over geological time. Climate studies were incorporating on solar luminosity. Even biological evolution was being reconsidered in light of the effects of interstellar dust and gas, the possibility that organic molecules might regularly arrive from other stellar systems. The implications extended to our understanding of Earth's uniqueness. If complex chemistry could survive journeys between star systems, then perhaps the ingredients for life were far more widely distributed throughout the galaxy than anyone had previously imagined. The building blocks of biology might be common currency in interstellar space, making the emergence of life less dependent on the specific conditions found in any single stellar system. This possibility was already influencing the search for extraterrestrial intelligence. Rather than focusing exclusively on radio signals or other forms of electromagnetic communication, researchers were beginning to consider whether evidence of alien life might arrive physically aboard interstellar objects. Microscopic fossils or complex organic molecules could preserve evidence of biological activity across cosmic distances and geological time. The techniques needed to detect such evidence were being developed in laboratories around the world. Advanced mass spectrometry could identify biological signatures in samples containing only a few molecules. Electron microscopy could reveal cellular structures preserved in ancient ice. DNA sequencing techniques could potentially decode genetic information that had traveled between star systems. These capabilities would be crucial for studying origins on Earth. If biological materials could survive interstellar journeys, then some future interstellar visitors, but they also had immediate applications for understanding life of the organic molecules found in terrestrial rocks, might have extraterrestrial origins. The boundary between Earth's indigenous chemistry and material from space was proving to be far more complex than anyone had realized. 3. iAtlas had also revealed the inadequacy of traditional categories for classifying cosmic objects. The comet didn't fit neatly into existing taxonomies of asteroids, comets, or planetesimals. Its combination of icy composition, radioactive chemistry, and rubble pile structure represented something entirely new in solar system science. Future interstellar visitors would likely prove equally challenging to classify, forcing researchers to develop new frameworks for understanding cosmic diversity. This taxonomic revolution was already beginning to influence how we studied objects within our own solar system. Researchers were discovering that many supposedly well-understood asteroids and comets showed subtle signs of exotic chemistry or unusual internal structure. The techniques developed for analyzing 3 iAtlas were revealing hidden complexity in familiar objects, suggesting that our solar system contained more diversity than traditional models predicted. The methodological innovations inspired by 3 iAtlas were also finding applications in other fields. The rapid analysis techniques developed for processing spectroscopic data were being adapted for medical diagnostics and environmental monitoring. The computational models created to track the comet's complex trajectory were proving useful for satellite navigation and space debris tracking. Even the international cooperation protocols developed during the 3I Atlas observation campaign were being adopted by other large-scale scientific projects. The seamless coordination between observatories on different continents had demonstrated the power of truly global collaboration in addressing complex research challenges. Educational institutions were already incorporating lessons from 3I Atlas into their curricula, but the impact extended far beyond formal education. The comet had captured public imagination in ways that few scientific discoveries managed to achieve. Children who had followed its journey through the solar system were growing up with a fundamentally different understanding of cosmic processes than previous generations. This shift in perspective was already visible in popular culture. Science fiction writers were crafting stories about galactic civilizations connected by networks of interstellar objects. Artists were creating works inspired by the beauty of ancient ice carrying memories across cosmic distances. Musicians were composing pieces that tried to capture the temporal scales involved in interstellar journeys. The cultural impact of 3I Atlas reflected something deeper than mere scientific curiosity. The comet had touched on fundamental questions about humanity's place in the cosmos and our connection to processes that operated on scales beyond individual experience. It had made the abstract concepts of stellar evolution and galactic chemistry tangible and personal. This emotional connection to cosmic processes was already influencing how people thought about environmental issues and long-term planning. If atoms could maintain their identity across billion-year journeys between star systems, then perhaps human actions could have consequences that extended far beyond immediately visible effects. The comet had provided a visceral understanding of deep time that abstract discussions of climate change and resource depletion had failed to achieve. The philosophical implications continued to unfold as researchers analyzed the wealth of data collected during 3I Atlas's passage. Each new discovery seemed to raise more questions than it answered, opening doorways to entire universes of possibility that hadn't existed before the comet's arrival. Perhaps most significantly, 3I Atlas had demonstrated that the universe was far more connected and dynamic than anyone had previously imagined. The spaces between stars weren't empty voids, but active environments where complex processes operated according to rules we were only beginning to understand. Matter, energy, and potentially information flowed constantly between different stellar systems, creating a galactic ecosystem that operated on timescales that dwarfed human civilization. This realization was already influencing humanity's long-term plans for space exploration and eventual expansion to other star systems. Rather than thinking of interstellar travel as a journey into unknown territory, we now understood it as joining an ancient migration that had been ongoing for billions of years. The galaxy wasn't empty space to be conquered, but a rich environment to be explored and understood. As 3I Atlas continued its journey into the cosmic deep, now beyond the reach of even our most sensitive instruments, it carried with it the knowledge that it had fundamentally changed how humanity understood its place in the universe. The comet had shown us that we were not isolated inhabitants of a single world, but participants in processes that connected us to every star in the galaxy. The story of 3I Atlas would continue to unfold long after the comet itself had disappeared from view. The data it provided would fuel decades of research. The technologies it inspired would enable future discoveries, and the perspective it offered would guide humanity's steps toward becoming an interstellar civilization. In every sense that mattered, 3I Atlas had not just visited our solar system, it had changed us forever. The final measurements from our most distant tracking stations painted a picture that would haunt astronomers for years to come. As 3I Atlas crossed the invisible threshold where our sun's influence gave way to the true interstellar medium, something unexpected happened. The comet's radio emissions, which had provided such crucial insights into its internal nuclear processes, suddenly changed frequency. The shift was subtle but unmistakable. For months, the radioactive decay within 3I Atlas's nucleus had been broadcasting at a steady wavelength, like a cosmic heartbeat marking time across the void. But as it entered interstellar space proper, that rhythm altered. The frequency dropped slightly, suggesting that the comet's internal chemistry was responding to its new environment in ways no one had predicted. Dr. Elena Vasquez, monitoring the signals from the Deep Space Network's most sensitive receivers, was among the first to notice the change. The data streaming across her screens showed something that shouldn't have been possible according to current models of nuclear decay. The radioactive processes powering 3I Atlas weren't just maintaining themselves in the interstellar environment. They were adapting to it. This adaptation hinted at complexities within the comet's structure that went far beyond simple nuclear chemistry. The interior of 3I Atlas appeared to be a dynamic system, capable of responding to external conditions in real time. As cosmic ray bombardment intensified in the unshielded environment between stars, the comet's internal processes shifted to accommodate the new reality. The implications were staggering. If 3I Atlas could adapt its nuclear chemistry to changing conditions, then it represented a form of cosmic evolution that operated on timescales measured in millions of years. The comet wasn't just a passive chunk of ice and rock drifting through space. It was an active system, capable of modifying its own behavior in response to environmental pressures. This discovery fundamentally changed how astronomers thought about the long-term survival of interstellar objects. Previous models had assumed that such wanderers would gradually lose their volatile materials and become inert over cosmic time. But 3I Atlas suggested that the opposite might be true. Interstellar objects might actually become more sophisticated during their journeys, developing internal processes that help them survive in the hostile environment between stars. The mechanism behind this adaptation remained mysterious. Perhaps the intense cosmic ray bombardment in interstellar space triggered nuclear reactions that couldn't occur in the more protected environment of a stellar system. Or maybe the extreme cold of deep space allowed exotic quantum effects to emerge, enabling forms of chemistry that were impossible at higher temperatures. Whatever the explanation, 3I Atlas had revealed yet another layer of complexity in the processes that shaped our galaxy. The comet wasn't just carrying information about its birthplace billions of years ago. It was actively processing new information, incorporating the experiences of its interstellar journey into its own structure. This realization sparked intense theoretical work among nuclear physicists and astrochemists. New models were developed to explain how radioactive processes might evolve under the extreme conditions of interstellar space. Computer simulations explored the possibility that cosmic ray bombardment could create complex feedback loops within the nuclei of wandering objects. The research revealed fascinating possibilities. Under the right conditions, the nuclear processes within an interstellar object might become self-organizing, developing structures and patterns that enhance their own survival. These cosmic systems might even exhibit something resembling memory, retaining information about their past experiences in the form of modified nuclear configurations. The concept pushed the boundaries of what could be considered alive or intelligent. While 3I Atlas showed no signs of biological activity, its adaptive nuclear chemistry suggested forms of organization that operated according to principles similar to those governing living systems. The comet was evolving, learning, and responding to its environment in ways that challenged traditional distinctions between living and non-living matter. As 3I Atlas disappeared beyond the range of our most sensitive instruments, the final signals it transmitted carried a message that would resonate through the scientific community for generations. The universe was not just stranger than we had imagined, it was stranger than we could imagine. Every assumption about how matter behaved in extreme environments had been challenged by this single object. The comet's departure left behind a transformed understanding of cosmic processes. We now knew that the spaces between stars were not passive voids, but active environments where matter geological timescales. The galaxy could evolve and adapt over just a collection of isolated stellar systems, but a vast laboratory where experiments in chemistry and physics had been running for billions of years. This knowledge would shape humanity's approach to future space exploration in profound ways. If objects could survive and even thrive during million-year journeys between stars, then perhaps human technology could be designed to do the same. The engineering challenges of interstellar travel suddenly seemed less insurmountable when viewed through the lens of 3I Atlas's remarkable resilience. The comet had also provided a roadmap for detecting future interstellar visitors. Its radio emissions had revealed internal processes that wouldn't have been visible through optical observations alone. Future survey programs would need to monitor the entire electromagnetic spectrum, listening for the subtle signals that might reveal the presence of active chemistry within seemingly inert objects. New detection networks were already being planned that would extend far beyond the traditional boundaries of our solar system. Arrays of sensitive receivers positioned throughout the outer planets would create an early warning system capable of detecting interstellar visitors years before they reached their closest approach to the Sun. These networks would provide the lead time necessary to mount comprehensive observation campaigns and potentially launch intercept missions. The technological requirements for such systems pushed the boundaries of current engineering capabilities. Receivers sensitive enough to detect the faint emissions from distant interstellar objects would need to operate in the extreme environment of the outer solar system, where temperatures approached absolute zero and radiation levels varied dramatically. Power systems would need to function reliably for decades without maintenance, while communication systems would need to transmit data across billions of miles of space. Despite these challenges, the scientific community was united in its determination to build the infrastructure necessary to study future interstellar visitors. 3I Atlas had demonstrated that such objects carried information about cosmic processes that couldn't be obtained through any other means. They were direct samples of the interstellar medium, time capsules from distant corners of the galaxy, and potentially carriers of information about alien worlds. The possibility that future interstellar visitors might carry signs of extraterrestrial life added urgency to these efforts. While 3I Atlas had shown no evidence of biological activity, its complex chemistry and adaptive behavior suggested that more sophisticated forms of organization might be possible in the interstellar environment. future objects might carry actual biological materials, preserved in the deep freeze of space for millions of years. Detecting such materials would require analytical techniques that pushed the boundaries of current technology. Mass spectrometers would need to identify biological signatures in samples containing only a few molecules. Electron microscopes would need to reveal cellular structures preserved in ancient ice. DNA sequencing techniques would need to decode genetic information that had potentially traveled between star systems. The development of these capabilities was already underway in laboratories around the world. Researchers were creating instruments capable of detecting life at the molecular level, devices that could distinguish between biological and non-biological chemistry with unprecedented precision. These tools would be essential for studying future interstellar visitors, but they also had immediate applications for understanding life's origins on Earth. The techniques being developed for interstellar object analysis were revealing hidden complexity in terrestrial samples as well. Meteorites that had been studied for decades were yielding new insights when examined with methods originally designed for analyzing 3I Atlas. The boundary between terrestrial and extraterrestrial chemistry was proving to be far more complex than anyone had realized. This complexity extended to our understanding of Earth's formation and early history. If interstellar objects regularly delivered exotic chemistry to young planetary systems, then Earth's early environment might have been far richer in complex molecules than traditional models suggested. The emergence of life might have been aided by a constant influx of organic materials from interstellar space. The implications reached beyond just Earth's history to encompass the entire process of planetary formation throughout the galaxy. If complex chemistry could survive journeys between star systems, then every newly formed planet might be seeded with the molecular ingredients necessary for biological evolution. Life might be far more common throughout the galaxy than anyone had dared to hope. This possibility was already influencing the search for extraterrestrial intelligence and the design of future missions to potentially habitable exoplanets. Rather than looking for signs of life that might have evolved independently on distant worlds, researchers were beginning to consider whether evidence of biological activity might have common origins throughout the galaxy. The concept of galactic panspermia, the idea that life might spread between star systems aboard objects like 3I Atlas, was gaining serious scientific consideration for the first time. While still speculative, the discovery of complex organic chemistry in an interstellar comet provided the first concrete evidence that such processes might be possible. These ideas were reshaping astrobiology research priorities and funding decisions. New missions were being planned to study the organic chemistry of comets and asteroids within our own solar system, looking for signs that they might have carried biological materials from interstellar space. Advanced life detection instruments were being designed for future missions to Mars and the outer planet moons. The search for life was expanding beyond traditional targets to encompass the entire population of small bodies in our solar system. Every comet and asteroid was now a potential carrier of biological information, a possible link in a chain of life that might extend across the entire galaxy. The implications for planetary protection protocols were profound, as strict sterilization requirements might need to be balanced against the natural exchange of biological materials that had been occurring for billions of years. As the last faint signals from 3I Atlas finally faded into the cosmic background noise, the comet left behind more than just scientific data and technological innovations. It had fundamentally altered humanity's understanding of our place in the cosmic order and our relationship with the vast processes that shaped galactic evolution. The comet had shown us that we were not isolated inhabitants of a single planetary system, but participants in a galactic ecosystem that operated on scales beyond individual human experience. The atoms in our bodies had been forged in stellar furnaces and scattered across space by processes similar to those that had launched 3I Atlas on its epic journey. We were literally connected to every corner of the galaxy through the fundamental forces that governed cosmic evolution. This connection was not just philosophical, but potentially practical. If matter could travel between star systems and retain complex chemical information, then perhaps intentional messages could make the same journey. Humanity's first attempts at interstellar communication might not involve radio signals beamed toward distant stars, but physical artifacts embedded in objects that were already making the journey between stellar systems. The concept of using interstellar wanderers as message carriers was already being seriously studied by researchers in fields ranging from material science to information theory. Ultra-stable storage media that could survive million-year journeys through space were being developed using techniques borrowed from quantum computing and nanotechnology. Error correction systems were being designed that could maintain information integrity even after exposure to cosmic radiation and extreme temperatures. These technological developments represented humanity's first serious steps toward joining the galactic community that 3I Atlas had revealed. We were no longer content to simply observe cosmic processes from afar. We were beginning to participate in them using the same mechanisms that had operated throughout the galaxy for billions of years. The legacy of 3I Atlas would extend far beyond its physical presence in our solar system. As the comet vanished into the interstellar void, it left behind a blueprint for understanding cosmic processes that had been operating since the galaxy's earliest epochs. Every measurement, every spectrum, every image captured during its passage represented a piece of a puzzle that was far larger than anyone had initially realized. In laboratories around the world, researchers were discovering that the data from 3I Atlas contained layers of information that hadn't been apparent during the initial analysis. Hidden within the spectral signatures were isotopic fingerprints that spoke of stellar processes occurring in environments unlike anything found in our local galactic neighborhood. The comet had carried within its nucleus a chemical library, documenting the history of star formation across vast regions of space. These discoveries were forcing astronomers to reconsider fundamental assumptions about how galaxies evolved over cosmic time. The traditional model suggested that chemical elements were distributed relatively uniformly throughout stellar systems, mixed by the turbulent processes that governed star formation. But 3I Atlas told a different story. Its nucleus contained chemical signatures that could only have formed in highly specialized environments, suggesting that galactic chemistry was far more heterogeneous than anyone had imagined. The implications rippled through multiple fields of study. Cosmologists began incorporating these findings into models of early universe evolution, considering how chemical complexity might have emerged in the first billion years after the Big Bang. Planetary scientists started questioning whether the materials that formed our solar system were truly representative of galactic compositions, or whether we inhabited a region with unusually uniform chemistry. Perhaps most intriguingly, the chemical diversity found in 3I Atlas suggested that conditions suitable for complex chemistry and potentially life might be far more widespread throughout the galaxy than previous models had predicted. If a single interstellar object could carry such an extraordinary range of molecular signatures, then the raw materials for biological evolution might be distributed across cosmic distances in ways that made life almost inevitable rather than improbably rare. This realization was already transforming discussions about the search for extraterrestrial intelligence. Rather than focusing exclusively on detecting technological signals from advanced civilizations, researchers were beginning to consider whether evidence of biological activity might be embedded in the very objects that move between star systems. The galaxy might be filled with a kind of biological internet, information encoded in molecular form and transmitted through the slow but steady migration of interstellar wanderers. The technological challenges of detecting such information were immense but not insurmountable. Advanced analytical techniques being developed for studying future interstellar visitors could potentially identify molecular patterns that indicated biological rather than purely chemical processes. The same methods might even reveal whether such biological signatures showed signs of intentional organization, suggesting the presence of intelligence. These possibilities were driving innovations in fields ranging from molecular biology to artificial intelligence. New algorithms were being developed that could identify patterns in chemical data that might indicate biological activity. Machine learning systems were being trained to recognize the subtle signatures that distinguished living from non-living chemistry, even when preserved in ancient ice for millions of years. The potential applications extended far beyond just studying interstellar objects. The same techniques being developed for detecting alien biochemistry could revolutionize our understanding of life's origins on Earth. They might reveal whether some of the organic molecules found in terrestrial rocks had extraterrestrial origins, or whether Earth's early chemistry had been influenced by materials delivered from interstellar space. As researchers delved deeper into the 3I Atlas data archive, they began to recognize patterns that suggested the comet's journey through space had been far more eventful than initially realized. Subtle variations in chemical composition throughout its nucleus told stories of encounters with different environments during its billion-year odyssey between the stars. So there you have it. 3I Atlas, the most extraordinary visitor our solar system has ever received. A cosmic messenger that shattered every assumption we had about interstellar space, about comet behavior, and about our place in the galactic community. This wasn't just another space rock drifting through the void. It was a time capsule from the deep cosmos, carrying secrets about stellar processes that occurred billions of years before Earth even existed. And in its brief passage through our neighborhood, it fundamentally changed how we understand the universe around us. If you found this journey through cosmic mysteries as fascinating as I did, consider subscribing for more explorations into the unknown. Until next time, keep looking up. Keep looking up.